I will build on the course of class modeling. So I will basically start more or less in the same picture. And what I will give today, because it's a tutorial, it's aimed for students, I will give some details on the metric that leads to Hunter-Saxton, which is the one that was the subject in the course, in the lecture of class. And we will extract exactly what this structure is. So there is a kernel, the kernel is well behaved, it's exactly the tangent space to the orbit, and so on. And this will be exactly the gauge invariant structure I would like to mention here. Let me phrase it like this. We will do here Riemannian structures, but we can do this for other type of pairings, like symplectic pairings or something, or even complex structure, and so on. So let me just give you the references which can help you to go into this kind of topic. So I will use, you will see the picture, actually I will show next, is coming from the paper of Kessin and Misolek, where earlier equations were derived, and in particular Hunter-Saxton on the homogeneous space given by the diffeomorphism preserving orientation of S1 and modulo rotations. The thing that I'm talking about actually is a long-time project with Steve Preston about different ways to endow a quotient with a Riemannian metric. So there is a paper already and a new one with more details. And I use this kind of ideas in shape analysis. So this is the original paper with where this idea was used. And the last, this one, gauge invariance of the degenerate Riemannian metrics, it's a very easy paper to read in Notices of American Mathematical Society. So if you want to have an idea of the ideas without technicalities, that's a good starting point. I will mention at some point a conjecture by Anne and Neb at the end, if I hope I will have time, which is related to this kind of subject. So let me show you this picture. So this is a picture that I took from the paper of Kessin and Misolek. And it's really the same kind of picture that we saw yesterday in the lecture of class modeling, right? So we have, here it's a group, but it can be also a total space of a fiber bundle. So there is a group K acting on some manifold. In this case, the manifold itself is a Lie group, G. And there is a subgroup, here it's denoted by K, acting on this. And so you have this fiber bundle structure, and the quotient map will map one of these fiber to a point in the quotient. And so there are different notation for cosets, action. We never know if you have to write a group on the right, on the left. It's a mess. And it's also a mess because in the literature there are two different conventions. So one is the one convention is the one used by Kessin and Misolek, which is this one. So you see G is modded out by K, so you write G mod K, but here the class is KG, so the reverse. There is another convention by Bourbaki, and this is the one that I will try to follow. I may make some mistakes, but which is the opposite one. So choose the one you prefer. I'm French, I will choose the Bourbaki one. But I mean, for the picture, you can just call this quotient space what you want, but the picture is the same. You have fiber bundle like this. The group is acting and on the fibers. And if you take a point here, you can act by an element of the small group K to map it on another point of the fibers. So the fibers are the orbits. Okay, so let's go back to the Hunter-Saxon equation, which is the following. You have seen it yesterday. And Klaas told us that this is a equation describing geodesic flow on the homogeneous space given by the diffeomorphism of S1, which are preserving the orientations, and the rotation of S1. So the group of rotation is actually acting, it's a subgroup of the diffeomorphism, of course, acting by rotations. And yeah, so it's this Hunter-Saxon equation describes geodesics for a metric which is a H1 dot metric. But this is a metric that we use. So this metric is first given at the identity of the group, and then we translate it everywhere by right translation. And you see that this metric is degenerate because any constant vector field, so meaning in the form CDX, here X is a parameter on the circle, but we identify the circle with, with R mod Z, for instance. So this constant vector will be killed because here we take the differential with respect to X first. Constant vector fields are therefore in the kernel of this pairing. So this pairing is degenerate, and actually only this constant vector belongs to the kernel. The kernel is exactly the space of constant. Are there some questions until now? Please ask questions. Okay, so let's go on. So what are these constant vector fields? These are the vector fields that are generated by rotations. So if you take a rotation on the circle, you will generate this kind of constant vector field. So the idea is to go to the quotient and exactly mod out the action by the rotations. So here again, mentioning that I'm using the Bourbaki convention where the small group here is on the left, the big one is on the right. So diff plus acts on the right on this quotient, the rotation acts on the left on this quotient. So it's a space of cosets, and a given coset is written like this. So you take a diffeomorphism and you look at all the diffeomorphisms that you can get by acting by a rotation on the left. So this kind of. For me, the rotation group is always at the same place. So the proposition is the following. We have a right invariant metric, and we want to know when it descends to the quotient, and actually everything can be, we can look at everything at the Lie algebra of the group here. So the invariance that makes the metric go down to the quotient is the add rot S invariance. Because the bilinear pairing that we have, the H1 dot bilinear pairing, is invariant by adjoint action of the small group. And the kernel of this pairing is exactly the space generated by infinitesimal action of the small group. It defines the Riemannian metric on the quotient space. And you can see this, I suppose I put, yeah. So first of all, how can we see that this pairing is invariant by the adjoint action of the small group, of the group of rotation? Well, as I said, here in this case, we identify the circle with R mod Z. And what is the adjoint action? The adjoint action by a rotation, you first do a rotation, then you do your diffeomorphism, and then you come back. So at the level set, at the level of the Lie algebra, you first do a rotation, then you do your vector field, which is an infinitesimal counterpart of the diffeomorphism, and then you go back with the inverse rotation. So you start with X, make a rotation, meaning you add an angle, theta. Sorry, I'm always pushing this. you start with the x on the circle, you rotate it, so here we are in the space of angles, so you're just adding a fixed angle theta. Then you look at the vector field at this point, x for theta, so I called it v. V is a function of the variable x. And d over dx is the tangent vector field to the circle, if you prefer. We add first with a rotation, we look at the value of the vector field there, and we come back by the inverse rotation, so meaning that we subtract the angle. Okay? So this is the adjoint action of the rotation by an angle theta on the vector field Vx dx. And if you look at the pairing with this H1 dot, the theta that is outside is killed because it's a constant rotation. And then what you get is this pairing here where the argument is shifted by theta, but you integrate over the circle. So you just change coordinate and you get the same pairing as before adjoint action. Okay, and the fact that this adjoint action preserves this pairing implies that this pairing go to the quotient. Now, what makes it non-degenerate on the quotient is the fact that the kernel is exactly, so the degeneracy of this H1 dot bilinear pairing is exactly the space of constant vector fields, so exactly the tangent space to the orbit. Yeah, so what you get downstairs, because you kill the kernel of this metric, you get downstairs a Riemannian metric. There's no non-degenerate one, because exactly the kernel is exactly tangent to the fiber. And when you project, you kill the direction of the fibers, and you get something non-degenerate. So this example is very, I think, easy to understand. I hope everybody understood it. If not, you can ask me a question right now. Because what I want to emphasize is that it's exactly an example of gauge invariance. Because if you look at curves on the quotient, downstairs, on the quotient, and you lift them and you compute the length, which is this functional, with respect to the H1 dot pairing, this length will not see the vertical direction because the vertical direction is in the kernel of this H1 dot. So any lift actually will give you the same value of this functional. So this length functional is actually invariant not only by rotation with fixed angle, but by time-dependent rotations. So if on this curve gamma, I act by a rotation which depends on time, here my time is between A and B, let's say. So what I'm doing is I take the curve gamma, which is in the top space, and at each time I'll act with a different rotation. Then the curve that I get will have exactly the same length. Why is it so? Because if you want to differentiate this new curve after a time-dependent rotation, well, you will differentiate to get the vector, the tangent vector of this curve, right? T appears in two places, in the rotation, which is time-dependent, and in the curve itself. So there will be two terms in the velocity of this path. One will come from the differentiation of the rotation with respect to time, and the other one will come from the rotation applied to the derivative of the curve we started with. So two terms. And the first one is by definition tangent to the orbit, because the first one is the infinitesimal action of the group of rotation at some point. The first one is vertical, and the second one you will get the derivative of the initial curve composed with some fixed rotation, and since the pairing is invariant by rotation, this will give you the same. Is this clear? Yes? Okay, so this gauge invariance, this name is coming from gauge field theory, of course. You have a gauge group, which is a group, for instance, of section of a principal bundle. Here, it's simply a group, here. Curves which map in a group, a time-dependent curve acting on curves in some total space. And the length is invariant by this action. Okay? So let me phrase it in a more general context, perhaps, where the total space is any manifold M, not necessarily a group. So in the previous case, M was the group of diffeomorphism of orientation preserving diffeomorphism of the circle, but we can extract this structure for any kind of manifold. Let's say, call it M. And we have a pairing, I call it G tilde, on the tangent space. So taking two tangent vectors, giving us a number, a bilinear pairing. This pairing is degenerate in the direction of projection. So in the tangent space to the fiber of a projection. So phi here is a fiber bundle of this total space M by over the base, which is the total space mod out by a group K. So we have this fiber bundle picture. On M, there is a degenerate metric, but the kernel is exactly killed by the projection. So the kernel is exactly the vertical space of this projection, so the kernel of the differential of pi. And in this case, it descends to a Riemannian metric on the quotient. So that's what we call here gauge invariant metric. And in this case, you will have the same kind of property. You can compute the length in the total space upstairs, and it will not depend on the position in the fibers. It will only depend on the curve which is projected downstairs. How can you build such a gauge invariant metric? Yes? Please.
K, because we have the column.
K was the group of rotation before, so it's a subgroup.
Okay.
Okay. Here it's just a group that is acting on M. And of course, you suppose that the quotient is a nice manifold, but we'll come to this. Okay, it's a group acting on M in such a way that K is a group acting on M in such a way that we have this fiber bundle structure, which is perhaps not completely trivial in infinite dimension, but I suppose we have this fiber bundle structure, and the tangent space to the orbit, which is exactly the kernel of this projection, is in exactly the kernel of the metric. So this is why it's descent to Riemannian metric downstairs. So how to construct this kind of K invariant metric on the total space M? Well, there are many ways, but one way is if you are lucky, you can have a vector bundle. I call it T because it's transversal. It's a transversal vector bundle. It's transversal to the kernel of the projection, which is called the vertical space. So perhaps I should go back to the initial picture. Perhaps I have it after? No. Another chapter. So the initial picture you have here. The vertical space is the one tangent to the fiber. The fiber are the orbit of the group. Here. So if you are lucky, you have like a vector bundle which is transverse to this vertical space. And if you start with a k-invariant metric M on the total space, you can define a gauge invariant one just by projecting onto this transversal. So how does it work? And what we get at the end is a non-degenerate Riemannian metric on the quotient. I will give more detail in the next slide. This is what we do actually. This is an example, but perhaps before I go to this example, I give you here. So suppose you have a decomposition like this. The total space of the manifold M, the tangent space 2M at a point, decompose into the vertical direction, which is a kernel of the projection, of the differential of the projection, plus a transversal. This kind of decomposition is automatic in finite dimension. It is not in infinite dimension. You may have a kernel here which is not complemented. This happens. But in this case, suppose you have this kind of decomposition. And if you start with a Riemannian metric which is k-invariant on M, then what you do is exactly this formula down here, downstairs. You define a metric of the quotient like this. If you start with two elements x, m, y, m, which are tangent at a given point small m in the manifold M, you will project them. This will give you two tangent vectors to the quotient. And any tangent vector of the quotient will be of this form, because we suppose we have a fiber bundle, so the projection is surjective, submersion. And the value of this pairing of these two tangent vector to the quotient will be given by first projecting on the transversals, so on T, and then pair these two projections with the Riemannian metric that we have on the total space. So of course, this projection will kill the vertical direction. This is the projection which is projection onto the transversal parallel to the vertical direction. This is a picture I wanted to show before, perhaps. Let me continue here. So this kind of pairing will define a Riemannian metric on the quotient. And it is clear because the tangent space to the quotient is isomorphic to the transversal. This part is killed. And this metric is non-degenerate on this transversal because we start with a Riemannian metric, which is not degenerate. What we do is simply we kill the vertical direction. So this kind of construction may make sense, may be useful when we have a natural transversal. And this is a picture that I wanted to show before here. For instance, for shapes, so 2D surfaces deforming in space, so, embedding of, let's say, the sphere into the 3D space. When you deform a shape, this means that you will deform it in all three directions in R3. But you can decompose this deformation into two parts. One which is normal to the surface, and one which is tangential to the surface. The tangential part is the one that is generated by the action of the diffeomorphism group. If you act by diffeomorphism group on a given shape, the infinitesimal vector field that you get through the infinitesimal action of the diffeomorphism will be tangent to the surface and will only induce change in the parametrization. So this is the vertical direction. here. And here there is a natural complement to this, because we are in R3 and we use the Euclidean metric on R3. And the natural complement are those vector fields that are normal to the surface. To make this decomposition, I didn't use any Riemannian metric. It's just a natural decomposition because of this embedding into R3 and using the Euclidean metric of R3. So if you start with any Riemannian metric on shapes, you can decompose the tangent space like this and kill the vertical direction here and just restrict the metric to the normal vector field. And this will give you a gauge invariant metric, which will not see the different parametrization. Is this clear? I have 2 minutes. Questions? I would like to make a connection with other type of theorem to endow a quotient space with a Riemannian metric. So there is a Riemannian immersion theorem. If you have a quotient of a manifold by a group and you are lucky in the sense that there is a globally defined section of the fiber bundle, then this section, if it's a smooth section, that it will define a submanifold in the total space. And if you have a Riemannian metric on M, you can restrict it to this submanifold, and this will give you a metric on this submanifold S. But this submanifold S will be isomorphic to the quotient through this section. So you can also define a metric on the quotient using this section. So the metric that you get on the quotient by this Riemann immersion theorem will depend on the section that you choose, of course, and on the metric that you started with. Here is a formula for this. This is another way to endow a quotient with a Riemannian metric. In the case you are lucky and you have a global section of your fiber bundle, which is not always the case. Another possibility is to use a Riemannian submersion theorem. So here it's a classical theorem of Riemannian geometry, but in the case where you don't have a complement, so the kernel of the differential of the projection is not complemented or not necessarily complemented. So in this case, you have to build the quotient space of the tangent space to the total space by the kernel of the differential of the projection. This is called the normal bundle, and you can use this normal bundle to endow the quotient space with a Riemannian metric. This Riemannian submersion theorem works also in the non-complemented case. And I will finish with an open question. For this, I need to recall that if you have a topological group G and a K, a subgroup of G, that the quotient of this group, so depending on which action you write it, G mod K or K mod G, the quotient is Hausdorff if and only if K is a closed subgroup of G. And the last slide is the following. There is a conjecture by Anne Nib, which basically tells you that you have a fiber bundle G over G mod K. So this is a conjecture. You suppose that K is a closed subgroup of a Banach in the Banach category, Banach-Lie group G. If K is a Banach-Lie subgroup in the sense that the structure of K is the structure of a Banach-Lie group with Lie algebra continuously embedded into G with a subspace topology, the conjecture says that it's equivalent to the fact that the quotient G mod K carries a structure of Banach manifold, for which the quotient map is such that the differential of this quotient map is surjective, and G acts mostly on the quotient. So you have a kind of fiber bundle here. It doesn't say if the fiber bundle is locally trivial, but anyway. So 2 implies 1 is already proved by Anne and Nib in their paper. As far as I know, the implication 1 implies 2 is still an open problem. So here in this, of course, if K is split, so if we have a complement to the Lie algebra of K, then we know that it works. That's, for instance, you can see it in a Bourbaki topology générale. It is also true if K is a normal subgroup. This is a paper by Glockner and Knapp, but in a general case, I think it's still an open question. Thank you very much for your attention.